Hello everybody, I'm Kaizhong. Welcome back to the second video of Bayesian analysis for time to event data. Today, I'm going to talk about some distribution and the likelihood function. Let's start with the exponential distribution. Here is the definition. A random variable t has exponential distribution with parameters theta greater than 0 if it has a probability distribution function theta times e to the negative theta times t. And here is the notation. For the exponential distribution, we know that the expected value is equal to 1 over theta, and the variance would be 1 over theta squared. In other words, the standard deviation is 1 over theta. How do we connect the exponential distribution with time event data? So, if the survival time follows the exponential distribution, then the survival function would be e to the negative theta times t. The hazard rate function is equal to theta. You can see that the exponential distribution gives the time to event data a very nice property, which is the hazard rate function is a constant over time and is equal to 1 over expected value. This is also called the memoryless property. In practice, the survival distribution is unknown and we need to estimate it from the data. One way to do this is by assuming that the survival distribution belongs to a parametric family, like exponential, Weibull, log normal, or gamma distribution. The other way is that we can take a non-parametric approach to estimate the survival distribution. For example, Cox model, which is also called proportional hazard model, is a very well-known semi-parametric model. But remember, both methods above are based on the following two assumptions. Independent observations yi delta I for I from 1 to n, and there is availability of information on the covariance of each unit. So, about the likelihood function, how can we obtain it for the ith individual? The following is the proof. First, we need to assume both event time t and censoring time c distributions are discrete. Let fi dot given theta and si dot given theta be discrete density and survival distribution for ti. Then let little gi and capital GI be discrete density and survival distribution for ci. Now we can write out the likelihood function for ith individual as being equal to the probability of ti equal yi and delta I equal 1 given theta. When delta I equal 1 and this likelihood function is equal to the probability of ci equal yi and delta I equal 0 given theta when delta I equal 0. Delta I equal 1 means it is an uncensored observation, so we can write it as ti less than or equal to ci. For censored data delta I equals 0, we know it means ti is greater than ci. Now we can take the probability function apart. When delta y equal 1, the ith likelihood function is equal to the probability of ti less than or equal to ci given ti equal yi given theta times the probability ti equal yi given theta. Now delta I equal 0, the ith likelihood function is equal to the probability of ti greater than ci given ci equal yi given theta times the probability ci equal yi given theta. Next, we replace ti by yi when delta I equal 1 and replace ci by yi when delta equals 0. As we can see, the first part of the probability ci is greater than or equal to yi is equal to the probability ci greater than yi plus probability Ci equal Yi. The probability Ci greater than Yi is capital GI. Probability Ci equal Yi is little gi. The second part here, the probability Ti equal Yi given theta, is the meaning for PDF f given theta. The probability Ti greater than Yi, we can write it as a survival function s Yi given theta. The probability Ci equal Yi given theta, we can write it as little gi. Hence, we can say that the i's likelihood function is proportional to the PDF when the data is uncensored and is proportional to the survival function when the data is censored. Now, for the general likelihood function, we just simply multiply the n individuals together. If we do a little bit of the modification, we can also see that the likelihood function is proportional to the production of the hazard rate functions and survival functions. After a lot of proofs, let's do some simple review to another two important distributions. One is the gamma distribution with parameters a and b both positive. It has the probability b to the a's power over gamma of a times theta to the negative a minus 1 power times e to the negative b times theta. Notice that theta must be positive here. If we have theta following the gamma distribution with parameter a and b, then we can conclude that the expected value for theta is a over v and the variance is a over b squared. A constant c times gamma follows the gamma distribution with parameters a and b over c. What's more, if a greater than 0, then the mode of theta is equal to a minus 1 over b. For a special case, if theta follows the gamma k over 2, 1/2, then we can see that theta follows the chi-square distribution with k degree of freedom, and here is the notation. If so, the expected value for theta would be k and the variance would be 2k. For the next video, we will talk about the one sample model, posterior analysis, probability interval for theta, choosing prior, and the prediction. I hope you enjoyed this video and see you guys next time.